Welcome back. We now start on chapter 7, Normal Curves and Sampling Distributions. Section 7.1, Graphs of Normal Probability Distributions. Here we are going to learn about how to graph a normal curve and summarize its important properties. Apply the empirical rule to solve real-world problems. One of the most important examples of a continuous probability distribution is the normal curve. This distribution was discussed by the French mathematician Abraham de Moivre, 1667 to 1754, and later by the German mathematician Carl Friedrich Gauss, 1777 to 1855, whose work is so important that the normal distribution is sometimes called Gaussian. The work of these mathematicians provided a foundation on which most of the theory of statistical inference is based. Okay, we want to look at the normal distribution. Let's figure out what it is. Applications of a normal probability distribution are so numerous that some mathematicians refer to it as a veritable Boy Scout knife of statistics. However, before we can apply it, we must examine some of the properties of a normal distribution. A rather complicated formula presented later in this section defines a normal distribution in terms of mu, that is the mean, and sigma, that is the standard deviation of the population distribution. It is only through this formula that we can verify if a distribution is normal. However, we can look at the graph of a normal distribution and get a good pictorial idea of some of the essential features of any normal distribution. The graph of a normal distribution is called a normal curve. It possesses a shape very much like the cross-section of a pile of dry sand. Because of its shape, blacksmiths would sometimes use a pile of dry sand in the construction of a mold for a bell. Okay, so that's the normal curve. Normal curve is also called a bell-shaped curve. So it is upward, downward, upward. What is this upward? This is the concavity. Okay, it is increasing and concave up. Here it is decreasing and concave down, increasing and concave down. Here it's decreasing and concave down. Here it is increasing and concave up. So these points where concavity changes from concave up to concave down, that's an inflection point. Here also, concave down to concave up. So that's an inflection point. Okay, mu is here. One standard of deviation away is where you get your inflection points. All right. We see that the general normal curve is smooth and symmetrical about the vertical line extending upward from the mean mu. So this curve is smooth. There are no pointed points, right? And symmetrical. Symmetrical means left-right symmetry about this line. That is, you could fold this page along this line and the two sides will match. Notice that the highest point of the curve occurs over mu. If the distribution were graphed on a piece of sheet metal, cut out, placed on a knife edge, the balance point would be at mu. So, if you had to balance this picture, you would have to hold it here for the two sides to balance. All right, that's what they are explaining there. We also see that the curve tends to level out and approach the horizontal x-axis like a glider making a landing. So as the curve goes on, it's getting leveled off towards the x-axis. All right. However, in mathematical theory, such a glider would never quite finish its landing because a normal curve never touches the horizontal axis. All right. So this curve, it keeps going low, but it will never touch the x-axis. The parameter sigma controls the spread of the curve. Sigma is your standard deviation. The curve is quite close to the horizontal axis at mu equals at mu plus 3 sigma, mu minus 3 sigma. Notice how the curve is so close to the horizontal axis around these two levels, right? Thus the standard deviation, if the standard deviation sigma is large, the curve will be more spread out. If it is small, the curve will be more peaked. Okay. So if sigma were small, that means this part would increase because sigma is, so pretend you can move these vertical lines closer to mu, then that would mean this will get taller more. So that's all they have said here. If standard deviation is large, the curve will be more spread out. If it is small, the curve will be more peaked. So if this comes closer, it will be more peaked. If these go farther, this curve will be more spread out. All right. So now it's cup upward or downward. Cup upward, it talks about concavity. This is cup up, upward cup or concave up. This is concave down, concave up. The exact places where the transition between upward and downward cupping occur are above the points mu plus sigma and mu minus sigma. So one standard deviation away, you notice how the concavity has changed. This is concave up and then concave down. Likewise, here it's concave down and here it is concave up. All right. So such transition points are called inflection points. All right. So the next videos I will start on my next slide. I'll start on the next video.